Hi, my name is Corbin Coyes. I'm the Vice President of Engineering for Q2ALS for North America, and today I'll do a presentation on solids. A lot of production engineers in the oil field right now are battling solids from our formation in our downhole rod pumps. So we'll talk quite a bit about that today. There's a crucial role in rod pumps, and through the rod pump system, the heart of the system are the valves and the plunger. So we're going to be looking at some of the guts of the different types of pumps, and we'll be looking at some of the properties of different types of solids and some different scenarios in the oil field where you'll have different different situations where these solids could become a really big issue when you're pumping the oil out of your ground. So we'll look at different strategies to separate solids and to move solids through the pumps. So here's a pump component breakdown. So I always like to show this. Our field guys are putting these pumps together every day. Some shops 8 to 10 a day. So just to look at some of these pumps at a detailed level, you've got your traveling valve, your plunger. I'll show you more about different types of plungers in a bit. Valve rod guide, we've got our barrel that goes across, and of course on the bottom you've got your standing valve that and your cage bushing that screws into your barrel. And on the top, this is a top hold down. We do have also a bottom hold down pump here I'm going to show you in a bit. But for the top hold down pumps, those are usually a little more shallow, and the bottom hold down pumps are run a little bit deeper into the reservoirs. And then in this case, you're looking at a horizontal reciprocation. We can do this now, but a lot of people run these vertically or in the band section. But what I want to bring your attention to is these two valves reciprocating up and down the seats, and the space between these valves and this side of the wall. So here's a memory test for everybody. I'd like you to remember the width of a dime is 0.7 inches, which is 7/1000ths of an inch. The width between an API ball and the rib of the cage is 0.045 inches or 45 thou. So this is the area in where the solids get trapped inside of our cages. So this is for API balls. Now alternative pattern balls, which are just smaller balls, we run those actually a little bit more because they give us more space in our pump. And we can only run these alternative pattern balls with the Vortex style pump, because if you don't, you'll see the damage that it does to the pump in one of the videos coming up pretty soon. So Q2 installs about 32,000 pumps per year in North America. Although I think it's around 54 pump shops now in every major oil field. So here's another question for you, and I will at the end ask you about this too as well. But why are our patented parts, why do they have a counterclockwise vortex to them? And so that's another question that I'll pose for you at the end of this presentation. So now we're going to go through a quick video, and after this video, I'd like to show you some data. So hang on after this, and I'll show you some numbers and why clearances are so important.
This video illustrates Q2's newest technology in our premium sand twister pump design. We utilize two of our patented technologies in this specialty design. As video illustrates, the flow of the gas and sand in through the strainer bushing into our patented Q2 Flow one-piece standing cage. The sand-laden fluids are moved through our Q2 Flow one-piece cage around the standing ball at maximum velocity using our tangent flow technology. Sediment is moved into the barrel chamber in a vortex. Attached to bottom of traveling cage is a positive seal plug. This is a specialty component that is manufactured with a -2 fit size. This tighter fit eliminates the sand from moving around the component alongside the plunger. The inside of the component has a beveled edge that forces the sand up into our Q2 Flow one-piece traveling cage using the tangent flow technology. Sand is then moved around traveling ball with maximum velocity, keeping sand in suspension in a vortex, discharging sands into the ID, the plunger, and then up into the premium sand twister component. The discharge ports in the sand twister are designed with the same angle as the Q2 flow cage, maximizing velocity. Sand is moved in the top portion of the barrel chamber through the discharge ports of component. Component is also designed with a -2 fit with beveled edge, disallowing sand to move alongside plunger. This beveled edge will also direct sand back through ports back into ID of plunger. Sand is then moved through rod guide into tubing column. This design utilizes a Q2 gas check assembly to help with both gas and sand issues. It works as a drop system that seals on the downstroke, disallowing the sand to fall back into the barrel chamber. Q2 is technology and innovation in motion, and with our ability to design our world-class product in-house, from concept to field application, is another example of the Q2 advantage.
All right, that was a wonderful video. Okay, so after looking at the tangent flow, Q2 flow, the sand twister, and the gas sand check valve, the numbers that are up on the screen now, our engineering department puts them together, and you see the pump size, and on here you've got the ball size and the part number. And for every single size of pump we have, there is an API ball, which is API standard ball, and that's a 45 thou clearance for traveling valves in general for most of the sizes. And then for the alternative pattern ball, you've got between like 0.17 or 0.165. So that's 170 thou difference in your clearance between your ball and your rip. And of course, this is the area that gets plugged up quite a bit with solids. Standing valve, same scenario. But on the bottom here, as you can see, I've actually done a quick calculation for you. With the clearance between the alternative pattern with respect to the API, we're 278% larger cross-sectional flow area with an alternative pattern ball. Now, this is really important as well. You can't always just fixate on cross-sectional area inside of these pumps. The Vortex technology is really one of the key elements that reduces your pressure drop in your pump. So here's a perfect example of a API to API with two different cages, and the pressure drop differential is around 36 to 42% at every flow rate. So the Vortex technology, what it does is it actually cups the ball in place. So with respect to the API ball, then the ball rattle isn't very big. But with alternative pattern balls, you've got more space. Without the Vortex cupping that alternative ball, you get a lot of vibration and a lot of pressure drop. So there's a great paper on the SPE journal, so the One Petro. The number's on the screen. So I recommend reading that paper. It's a very well done paper with field data, theoretical information, and as well as of some of the lab testing that was done as well. So I believe, and I've always believed this, that every good idea is born in the field and then modified in the lab. A lot of engineers have that reverse. They try to dream up something in the lab, spend a lot of money, a lot of time, a lot of research, and they make something that's expensive, that maybe flows really well, but it's not structurally sound, or vice versa, right? You can only do so much CFD and FEA with designs that aren't used in the field. So a lot of our pump shop managers, that's where they come from. So our communication with them is extremely important. So really quickly here, I'll show you a lab test that we did at a college, and to show you the vibration of the alternative pattern balls inside of a cage. And you can see that it's not very much, but when it comes down to the other balls, they really rattle quite a bit in the cage. So we'll show that video now. Hi, I'm Corbin Coyes from Tangent Flow. Here's an experiment with an 1 3/4 API insert with an alternative ball, and you'll see it's going at 20 gallons per minute, and it is not rattling and seated perfectly. This is the ID of the ball. It's a 1-inch alternative ball. The ID of the 1 3/4 insert is 1.165. There is 165 thou clearance between the insert and this alternative ball. So there you have it. There's the valves that actually can handle some solids, okay? Another lab that we've just built in-house here, we spent a lot of time and energy on it. We decided to look at the vortex fluid flow behavior and find out how long it went, how it carries solids and small gas molecules after it hits the valve. So we set up a flow run test, and actually really interesting, we actually had a scientist come up and inject some nanobubbles in there, because the bubbles that we are experiencing in our pumps downhole at 8,000, 10,000 feet, they're really small. So it was neat to be able to look at that median in the flow run, because I can't pressure it up to 2,500 PSI and get the pressures, but at least I can look at some of the media that we're using inside of our pumps and understand how that behaves with our valves. Yeah, so in this case we have acrylic tubing, we've got pressure sensors connected to a PLC, and the really interesting thing about that is we were able to measure the differential pressures with respect to different flow rates, and we're able to simulate reciprocation in the well. So that's really important for us, because we're non-steady state. We're always pumping, and you're accelerating the fluid and deaccelerating the fluid. In this case, what you're seeing is the HVS valve. So this is the first pump that you can actually pump down to 90 degrees. In the past, these balls fall off the seats around 45 degrees. So we've been limited how far we can go. Now we're getting down to the bottoms of these horizontal wells, and with that extra fluid level, you're getting better pump intake pressure, and you're actually getting better production out of your wells. So it's been really interesting to see these work in the field. I think we've got about 1,500 now in every oil field, and we're just engineering around the HVS valve now for dog leg, severity, for friction, and for all the wear parts around it. And I have a question for you. Have you ever been to a flow run? Have you ever seen what a flow run can do when it comes to modeling artificial reciprocation? Like I mentioned before, Vmax is actually equal to pi times V average. So say your average production in your well is 200 barrels a day. Well, guess what? You accelerate to 800 in that stroke of your rod pump. So it's interesting, because that's definitely non-steady state. And we have to engineer our pumps and our operational services on surface, all of our POCs and everything else. And with respect to solids transport and gas, we have to take this in consideration for sure. So just wanted to make sure we pointed out that phenomenon is there, and you can read that in SB papers. That's a really good read as well. Pi times VAV. Now when it comes to solids, so we always try to get more data from our pump shops. When a pump comes in and say it is plugs with solids, the first thing we do actually is meet with the client and say, okay, what were the operational procedures? What's the overall solid strategy for fracking these wells? Is it native? Is it frac sand? Is it sand that's used to erode the fractures downhole to create more permeability from your fractures? And do you run liners? Do you do clean outs? So we ask all this information. But if we do get a pump that has solids in it, we take a sample and we do a D50 particle size distribution curve. So what this gives us is, it gives us the size, the average D50, the diameter of the 50% line of the distribution of solids. And from there, actually, if you go back to skin factor in your old production engineering books, when the drillers come through, they actually try to plug off these pore spaces, and they do so by using the 1/3 size theory and the square root of permeability. So basically all that means is that if you've got a pore space and you've got a sand particle that's 1/3 that size, and you've got other well-graded material that can pack behind it, that's the perfect way to plug off a pore space. So we don't want to do that. So we want to measure our solids to make sure that they're not plugging up some of our pumps downhole. So particle size distribution curves are very valuable for us in the field. Now everybody, I'd like to get you back to the old days of these formulas you learned in engineering. So Stokes law. Do you remember that theory? So I know that engineers do, and I know that the drilling men, the drilling fluid men, mud men do. This is where the formula of, you know, settling rate under the force of gravity for solids. The particle is another part of it, another part of the formula. The gravitational constant is in there, and the density of the solid. And then, of course, the viscosity, the carrying capacity. But with Stokes' law, you have these variables with respect to settling. And in our world, you know, sometimes it's good to go to the other worlds like drilling and you know, the settling and the environmental guys to understand how they separate solids. And the drilling side is really interesting. So the first thing that they do is they use shaker screens, right? And they use elliptical shaker screens of certain sizes, and that takes out the majority of the solids. And then the second thing they do is they use settling ponds or sumps. Back when I was on the rigs, they used sumps, but now it's tanks. And that gives you the time you need to be able to settle some of the solids. But then the really fines hang out still in there. And of course, at the end of it, you've got a centrifuge. So these centrifuges run at like 1800 to 3600 RPM. That spins out the fines inside the liquids. And then from there, you've got your nice liquid with your polymer. You add some more, and then you head down, back down hole again, and continue to drill the well. So it's interesting because they know that the fines takes high G-force to be able to separate out the solids. And are we doing that on the production side? Do we have that kind of G-force available to us when solids are settling down a pipe? That's a question that some of you might want to ask. Is it really doing what it should? The high gas rate. So this is something on the operational side that we've seen. Now that we're starting to discover deeper into the wellbores, we're starting to start with 70, 80 degrees, 8,000, 9,000 feet in the build sections at the end near the horizontals. We're finding that actually that fluid level in the pump is so important. And for a long time, actually, some of the tubing anchors have really plugged up the wellbore up hole. So your fluid column can go all the way upside of your casing and tubing, thousands of feet. And that comes down and acts on your pump as well as the reservoir pressure that comes in. So with the tubing, sometimes you get gas trapped below there between your pump. And you're not getting the pump intake pressure that you really need to be able to get good pump fillage to your pump. So it's interesting to look at different types of tubing anchors to give you more fluid level on your pump. So that's going to help you with your solids. And the reason I say this is that once you get a flush of gas that comes in the horizontals and the build sections, guess what? High velocities, that's going to bring a slug of solids with it, right? When you have just liquid and its flow rate, you'll see that actually that solid accumulates on the bottom of the wellbore, and I'll get into that slide in a bit. But once you have a big flush of gas and oil and everything that comes up, that transports all of that solids that have been peacefully laying on the build section and the horizontals for a long time, and that's usually when we see these pumps lock up. So startup procedures, casing pressure, tubing pressure, when you start these up, very, very important. This slide here is interesting because we took some information from the drilling guys and said, well, your first line of defense is screens. Well, in the production world, you know, in this type of geometry, it's very difficult to run a screen, right? Because as soon as they plug up, you got a small cross-section area, the screens plug up and then you starve your pump. So we thought, well, why don't we develop a device that's self-cleaning? So when you stroke your pump up and down like this, you always have a part down below where you actually have no movement and the solids can settle out. So below this, you enter basically a drilling shaker screen, sized for your solids, and then the standing valve here on the downstroke, when the travel valve comes down, there's a pulse that actually occurs with that ball that comes down, and that pulse temporarily lifts the solids off that screen, and they settle out of into the mud joints. So we've been experimenting with this. It's pretty interesting. You've got vertical wells and your horizontal wells. And when it comes down to the vertical wells, you know, gas separation actually, if you've got, you know, high GLRs, it's really important with respect to solids. First you separate the gas, number one, then you separate out the solids. And the solids actually, in some cases, like a little bit of spiral flow, maybe not too much centrifugal flow, but a little bit of a swirl vane is probably a good thing when it comes to separating out some of the solids and then leaving something that you can pump up through the middle to the pump to get good fillage. We're also experimenting with these horizontal separators, and it's interesting because we think that little small cavities would help distribute more of that flow that comes up. So you get little kind of cavities that are inside the system, and when the fluid comes up, it takes a little bit of that solids at a time and feeds it to the pump. So there's a few suppliers that have that available out there right now as well. Here's an interesting slide when it comes down to the ability of controlling slugging. So this well, as you can see, a lot of variation with respect to slugging. And I want to point out the strokes per minute on top and also the pump village up top. Two things happened here. We used a separator that had enough capacity to be able to handle some pretty high rates. And we also used a tubing anchor that gave us more fluid level to our pump. The other thing that's really interesting here is that when you're pumping these wells and you're at an angle, the POC and the person out there operating, you know, looking at the variable frequency drives and the pump off controllers, and you know, even aligning the magnets on hole. Some of our really experienced guys in the field can come to a site and modify a few of the parameters on surface to really help the separator down hole make sure it's capturing the gas, and to really look at the type of stroke length that you need in order to get that really good fillage, right? And you know, with respect to the dog legs and how some of these wells have, you know, some curvature to them and some friction, you have to have a really good experienced guy to come on the rig to play with these parameters. It takes a few hours, but I mean, some of these operators can go on site, and we've got a gentleman that does a very good job at, and he can increase the instantaneous production by, you know, 20-30% just by modifying things on surface if you have the right tools in the ground to begin with. So just to back up, I'm going to go look at these really quick, and I want to talk about some of the heart of the system. So the turbine is a seat plug that comes on to the standing valve here, and that generates a vortex and accelerates the fluid to the outside where the ball is, where that smallest cross-sectional area is. So you're able to get just more acceleration through the smallest cross-section of your pump, and not have it hit that ball straight on. So that's the turbine. It actually looks like a jet turbine engine. And then under that, after that, you've got your vortex flow. So these pumps have been around forever. Most companies are going to vortex flow now. They've been around for 20 years. We use them in every one of our pumps, and it has been a standard. The only difference is now with the single, now we have the double that's going down into the horizontals and helping with pumping more oil out of the ground in the horizontal wells. The plungers, now there's different types of plungers. In this case, I'll just point you towards this. This here, for example, is a bottom hold down, right? So, and you've got a spray weld plunger on here. And then you have a Monel pin up here as well. And then this is your, this is sometimes where some of your sand comes down and falls down the side of your plunger. This is not a sand twister. A sand twister is very similar, but it has wormholes that come up, beveled edge, so sand can't get caught in there and does not come down and score your plunger. But even sand does come down here, these little grooves kind of help a little bit, right? Because this could be a really nice tight fit. This can be, you know, anywhere between a 2 thou fit and a 12 thou fit. Normally they're around 8 thou if you have some solids in there a little bit deeper. And you can see on this particular one, this is a smaller pump size. I think it's 1.5 inches, and this must be 1.75 inches, I think, with a 2-inch standing. But this one here is a top hold down, And you can see in this configuration they have a lot of grooved, and these are grooved plungers here. So this helps too as well, because the sand doesn't come in and score the inside of your plunger against your barrel there too as well. But you know, we also actually recommend certain types of barrels for sand. I know the chrome line barrels, I think it's called King Chrome, is one of the best because it's got a dual layer of chrome. So your microfractures chrome always has small microfractures. In this case, if it's a dual layer chrome, then those don't line up. So you can't get corrosion through those small cross-sectional areas and have the galvanic corrosion get you in the end. And you know, on this one here, I think there's a Q2 flow plunger adapter up top as well. That turns the fluid here. Any way we can turn the fluid through these pumps to get all of the solids distributed around the annulus properly. This example here, you can see that the solids would come down here and it would actually come on this ledge, and we don't like that. So we'd like to have it turning all the way through and up through here as well, just to keep it suspended in the vortex. So here's the memory test. If you lasted this long, congratulations. I know this has been, I've gone through a lot really quickly, so you can go back and review some of this, and please call me if you have questions. But for the memory test, what was the width of the dime? All right. 0.7 of an inch, you are correct. That's 700 thousandths of an inch. That's the width of a dime. And if you remember, the API clearance is 1/15 of that. So that's a 45 thou clearance. An alternative pattern ball is 3 times that of an API ball, which really helps us with our solids, but you need to use the Vortex technology with the alternative pattern ball, or it will beat out your cages. Now, if you remember at the beginning of the presentation, I asked you a question. It was, why are the vortexes clockwise and not the other direction, counterclockwise? Well, originally we did some counterclockwise turns in here, but some of the structure factors hurt us. What happens on these pumps is you always turn the pipe in this way when you connect the pieces. So when you turn the thread together, any kind of piece that has a clockwise vortex, you're going with the thread. So it's not only fluid flow that we have to really worry about, it's also the structural and the strain and the pressure we put on our vortex valves. So there's your answer, and I know I promised that to you. We do have a really interesting app that you can download and have a whole bunch of university type style. I think it's called the Q2 University. But they're an hour and a half, and they're level 2 and 3 production courses. So if you're sitting in your car and you want to play them, you don't need to see the video. You can hear the conversations happening, or if you want to see them at home, that's available too as well. And you also have an AI machine on our new phone that looks at a snapshot of a dyno and says there's a good chance you have fluid pound, you've got gas interference, you have a travel valve that's not that's sticking, or what have you. So it gives you an idea of what's happening in your well. It's a really interesting app. And I think that's it for today. I just want to say I really do enjoy educating production engineers on the different tools that we have, you know, in the industry. And if you have time, please reach out to me, because I've got a flow run that's really good for demonstrating different types of flow and different types of valves. And I'll be more than glad to come visit you and set that up in your area. So thanks very much. Appreciate your time.